Hi guys, today we're going to showcase an exciting A-level required practical on stationary waves. Just a quick heads up.
We know that our educational maths and physics videos may not be for everybody, and we sometimes lose subscribers.
But don't worry, we'll continue creating a variety of content that you've subscribed for and enjoy.
We do believe in the value of these educational videos, and we'll continue making them alongside our other content. Thanks for the support and understanding.
If you're not doing A-level different course or different country, then it's all physics, so you'll be doing something related.
Before we get started, we've got a great opportunity for those of you who want to make this at home. So we made all the equipment at home, so you don't have to spend extra money on expensive equipment.
It was about the price of a pizza.
Yeah. Really simple to make. We've got another video on that. Yeah.
You can also make other things with it, the vibration generator, like waves with water. So that's one video making the vibration generator. That's short, 10 to 12 minutes. Another video on messing around, showing the full setup, messing around with the vibration generator.
Show you guys how a solenoid works.
Yeah, we make a solenoid.
Take apart the solenoid as well.
And then this video, which is just going through the experiment, all the maths and everything will be at the end. So it's more technical, this video. So if you're wanting more of the fun stuff, then go to those other videos. It is fun, but at the end we do go quite in depth in like the maths, rearranging the equations, analysing the results and all that sort of stuff. But yeah. We've put all the data and the formulas and everything in a spreadsheet, which we've shared with you guys, so you guys can edit, put your own data in, and it plots the graph, works out all the stuff that you need.
So let's get started.
We've got the teacher and technician sheet here, which is really useful for us to have. And we've also got the sheet you'll be given as a student, with a diagram, everything. And we're just going to take you through this and the experiment. So let's go through the materials and equipment. So we need a signal generator and vibration generator. So that's this thing here on the diagram. And at school, this is probably about £100 or so, a bit more worth of equipment, which we've replaced with this super simple setup. It looks a bit like spaghetti right now, but this is just a diagram. It's really simple. You've just got a battery, 1, 2, 3, 4, 5, 6 components. You don't even need that.
You can get the components off places like Amazon, AliExpress, eBay for under £20.
Yeah, got it from AliExpress. It might be a bit later than the other one, so
yeah. So you just need to connect it all up. And we also use a breadboard as well, so that you can just take these pieces out and reuse it for other projects. We've got loads of other videos that reuse these components because they're super common components. Like you said, you can pick them up places like Amazon, eBay. If you were interested in this, we've got a really in-depth, detailed video telling you how you can make this, if that's something that you want to do. But not in this video because you might just want to get on with the experiment. So that's that. The next thing that you'll need is here stand and 2 kilogram balance mass counterweight, which is on this diagram here. There's the stand. We've just replaced that with just an Allen key, I'm not sure if you can see, and a clamp there. Really just needs to be attached to something that's not going to be moving. The next thing is 1.5 or 1 meter length of string, which we've got here. We've just used about 1 meter, which is self-explanatory. Yeah, I'm just on the diagram for reference. That's this thing here. You can just see it moving once the whole experiment is in flow. Next, a pulley which can be clamped to the bench. So that's this, which is just an old Lego thing, old Lego wheel that we found. And then clamps. Oh yeah, Poundland clamps as well, just to keep everything fixed so it doesn't move. That's the Poundland clamp. A wooden bridge slightly higher than the pulley. That's this here. Set square on a box. Yeah, set square on a box. If you just want to look at the diagram as well, there's the pulley there. There's the movable bridge. Next thing, 100 gram masses on a holder. So on the diagram, we can see that's just there hanging off the pulley. And hanging off the pulley here, we have just got this raincoat bag with some batteries in. The final thing, we need a meter ruler. I'm not sure that's in the diagram. So we've just got this meter ruler there and there. We've got a few options. And then finally, an electronic top pan balance with a precision of 0.1 grams or better. So we've just got this, Amazon, £3.
It's even better than that one.
It's even more accurate, yeah.
It's 0.01 grams.
Yeah. So yeah, that's the setup. Let's get on with the experiment. So what are we going to do in this experiment? Well, we've got tension in this string from the masses pulling it over the pulley. Now that's going to stay the same throughout the full experiment. So later on, we can measure the mass, take some measurements and work out the tension. Now we can change the length of this string using our wooden bridge or our set square on the box. And then we also are going to vibrate the string by just pressing this button. Hope you can see it's vibrating. And you can change the frequency by turning this dial, and it will display the frequency on this screen here. So for each length of the string, the frequency that we're wanting to find is the fundamental frequency. Now, that is when, if we show this diagram, that is when the string, when it's vibrating, should look something like this here, which is also called the first harmonic. And if you can see here, this is these points here are called nodes, and that's when the string looks like it's just not moving, it's just in a fixed position. And then these points here, 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 these are the antinodes, and that's when the string is oscillating at its maximum. And that's what we're trying to find in the first harmonic. We want to find where these 2 points here are at their maximum. So we'll keep changing this frequency, the frequency of our string with this dial, until it looks like our string is oscillating at its maximum. I won't go that high, but at its maximum, it should be in the center here. Then we'll just change the length of the string with our little wooden bridge, measure the frequency, the fundamental frequency again for that length, and then just keep repeating that for different lengths of the string. Then record that, repeat it again just to increase our accuracy, so we can find an average. And yeah, that's the experiment. And then also as a little extras, we don't have to do this. I don't think I didn't do this at school, but we're also going to find the second harmonic. So that's when this string should look something like this when it's oscillating, and then also the third harmonic, so it should look something like that as well. So anyways, let's get on with the experiment. So here you can see we've got our wooden bridge, fake wooden bridge at 905 millimeters. We've already taken one of our measurements. We won't bore you with all of the measurements, but this is our second one at 905 millimeters. So let's press this to start the frequency generator. Press. It's vibrating. I'm going to turn the dial to change the frequency. So that looks really good. What's that? 20 hertz. That looks really good. I think that's probably the first harmonic. Now that's the first harmonic. We did say that we would try find the second and third harmonics. Let's try the second. So that should be about double this frequency, so about 40. So let's start increasing the frequency. Oh, that's decreasing it. So we're at about 30 now. I mean, you can see that it's not even moving. This doesn't even look like it's moving very much. So let's keep increasing the frequency. I think I can see the start of... Yeah, it looks like it's starting there. Oh, that's looking good. Let's go to 40, because that's what I'm expecting. Oh, no.
Back down.
Go back down. So let's try maybe 39, do you think? I think maybe 30. Do you think whoa, it looks like it does look like it's settled. So I was expecting it to be 40, but I mean it looks like it's settled at 39. But that's close enough. So I mean this looks like it's a node right here. It looks like the string's hardly even moving at all. And you can see this looks like it's the antinodes here. I mean, if you just look at the diagram, this is the second harmonic, and I think our string pretty much matches that description. You see the antinodes, the antinode, the node there, the node there. Now let's see if we can find the third harmonic, so it should match this sort of diagram here. So let's go and it should be about 60, I'm reckoning, maybe a bit under, because we were a bit under 40, weren't we? So, I mean, the string doesn't even look like it's moving anymore, like when it was at 30 hertz. Oh, yeah, that looks like, whoa, I think I can see it. It looks, I mean, it's at 58 right now, but it does look like that's the third harmonic. You can see the node there, the antinode there, the node here. I mean, the string looks like it's not moving at all in real life. I'm not sure what you can see in the camera. Another antinode, so there, and then another node here, antinode. So that is pretty much matching the description of the third harmonic. And what's it at? 58. So that's super close to 60, which is what we predicted. So it's pretty impressive. I might just try 60 to see what it looks like. Whoa, I've put it at 60. I didn't expect that. I've put it at 60 and it's perfect. We'll repeat that with some different lengths, record the frequencies and get back to you.
So we've got our results now, and at school you would put your results in a logbook and graph it all out, do all the calculations by hand. But we're using a Google spreadsheet, so then you can have this in your browser, look at it, duplicate it, put your own results in and have a little mess around with it. We do have a great video on Google Sheets taking you through a beginner to being able to do stuff like this. So that's making graphs, using formulas, etc. So go check that out. Go check that out if you want to. So now let's take you through our results.
Here's our spreadsheet. Yours may look a little bit different as we may improve on it, but it will broadly be the same. So let me show you around. This first column is all the string lengths that we tried. These are the frequencies of the first harmonic we measured for each length. Here we repeated the whole experiment for accuracy and noted the frequency. The next column is the average frequency, which in our case is a bit redundant as we got the same results in our repeat, but the formula's there for you guys to use. Now, this is when you guys joined us in the video. It's when we measured 0.905 meters and 20 hertz for the first harmonic. Hopefully that rings some bells. Okay, now who doesn't love a nice graph? And we've got two here for you. Now the one on the left is the one we used given the information we were given on the student sheet download, which we found is a bit unnecessarily involved and a little bit confusing too. On the right is the alternative method. It's a bit simpler. It's also the one that I did at school.
This is the equation that ties all the variables in this experiment together. So let's have a little closer look. This F1 is the frequency of the first harmonic. That's what the 1 stands for. That's equal to 1 over 2L. L is the length of the string. Then we're multiplying that by the square root of T over mu. This funny character here is mu. This T is the tension. We'll look at mu later, but let's work out the tension and get that into our spreadsheet.
Here we are measuring the mass of our back with all the little masses in, or batteries, and then I just marked the string where it was going off the edge of the pulley, and so I've just put that amount of string on, and you can see that it's 95.01 pounds. We need this mass to measure the tension of the string. We work out the tension of the string by multiplying the mass by the acceleration due to gravity, which is called little g, and that's around 9.8 meters per second squared. Here on the spreadsheet, we've got the mass here, then beneath it, it's the tension that the spreadsheet has worked out for us. But if you're not using the spreadsheet, you can simply do that by timesing the mass by 9.8. Now that mu, what is it? Well, mu is mass per unit length of the string. Now, what does that mean? Well, here I've got a meter of the string we used, and it's just what's the mass of that meter of string. And from that, we can work out the mass of 100 meters of the string, or half a meter, by multiplying it by 100 or a half. Where does this 2L come from? Well, down here, we've got the first harmonic here, and it's just a fact that, really far down. It's just a fact that between any two nodes is half the wavelength. This is a fact whether it's the first harmonic, second harmonic, third harmonic, two adjacent nodes is half the wavelength. This little upside down y here is called lambda, and that is usually used to represent wavelength. So this is the length we're measuring, the L that we're measuring. And if that's half a wavelength, then 2L would be a full wavelength. So that's where the 2L comes from. On this graph here, we've got 1 over the frequency on the Y and string length on the X. And as my sister said earlier, we've got a simpler graph over here. And we've got frequency on the Y and 1 over the length on the X. Now, on either of these graphs, you'll be asked to draw a line of best fit. Now, we've made Google Sheets do this for us, but if you're drawing the line of best fit by hand, you want the line to go through the origin here, and you also want the same amount of points above the line than below the line. Now, to figure out the gradient of these lines, we've made Google Sheets do it for us again, here for this graph, and then here for the other graph. But again, if you're doing this by hand, then it's simple enough. You just pick 2 points on the line and do the change in y divided by the change in x. One thing we can work out with all of this is the wave speed. So if you come over here, we've got the formula for wave speed, v equals f lambda, v being the speed, f being the frequency, and lambda being the wavelength. Now this kind of makes sense, doesn't it? Because if the frequency was 20 hertz, that's 20 wavelengths per second, and the wavelength, lambda, was 1 meter, 20 times a meter is 20, so it'd be 20 meters per second. Makes sense. So if we come up here to our simpler graph, just zoom in, there we go. The gradient represents the frequency divided by 1 over L. Now this is the same as the frequency times by L over 1, which is the same as the frequency times L. We have the equation V equals F lambda. Now we've got the F, that's fine. But how do we get lambda, the wavelength, from the length of the string? Well, if you remember, we said earlier the wavelength is just double the length of the string. So we just need to double that. So it would be 2FL. So if we come down here, we can see we've got our gradient here. And we've just doubled it here to get the speed. So the speed is nearly 36 meters per second. During the experiment, the wave speed stayed the same. This is because mu was the same because we used the same string, and also the tension was the same because we used the same mass. Now you can work out the wave speed with the other graph here. Like we said earlier, we think this method is a bit more involved than the other method that we just did. But just for completeness, here is my working out. You can pause the video and look through it if you want. But briefly, m is just the gradient. And we worked out that if you get 2 and divide it by the gradient, then you'll get the wave speed. So if we go down here, here's the gradient. And over here, the spreadsheet has worked out 2 divided by the gradient,
which is 36.729. And that is close, but not exactly what we got on the other graph over here, which is 35.915. It's really interesting to me that we can find out the wave speed by just using the tension and mu. We can do this by mixing these two formulas together. So we'll start with this formula here. And instead of this F frequency here, we'll use this frequency. So I've just substituted that in down here. So here it is. So we need to multiply this still by the wavelength. And if you remember from earlier, the wavelength is also just, sorry about that, 2L. And these cancel out. So we're left with the wave speeds equaling the root of the tension divided by mu. So we can calculate the wave speed with just the tension and the mu and see if it agrees with what we've just calculated earlier. So we know the tension, but then we'd have to put a meter of string on the scales to find out mu. But before we do that, let's try work out mu and see if we can predict what mu will be before we put the string on the scales. This was my starting point, and I multiplied both sides by 2L. This got me here. FL, if you remember, is the gradient from this graph. So I just replaced FL with M, which is the gradient. I squared both sides and then rearranged to find mu. These two things are the same thing, but this is what's in the spreadsheet. So the spreadsheet has got the tension from here, which was 0.931 newtons, and it's got the gradient from here, which was 17.957, and it's used this formula and put it into this cell here. So if we put a meter of string on the scales, it should be 0.000722 kilograms or 0.7 grams. So you can do this on using the other graph, like we've done here. The formula is the tension over 4 times the gradient to the power of 2. And we got 0.00069 kilograms or 0.69 grams.
So we're just measuring the mass of 1 meter of our string, and it's 0.69 grams.
That's exact with our calculation, if you can see here. And then the calculation with the other graph, we are nearly spot on. We're close. So we calculated the mass of a meter of the string just by knowing the tension and the frequencies that we measured for the first harmonic at different lengths. So by plotting those lengths and frequencies on a graph, we were able to work out the velocity, speed of the wave. And we said we're going to check that just by using the tension of the string and then also the mass of a meter of the string, which we've just measured. This is the formula that we put into the spreadsheet. And here is what the spreadsheet's worked out. So that's pretty close to what we calculated using a completely different method. Wow, that was a lot to take in.
You might need to rewind or rewatch some of this video. We know we would.
We know that also a lot of physics teachers, professors and geniuses do watch our videos, so if you think we've missed anything out, left anything out of the video, let us know in the comment section down below. We'll compile it all into an article.
Yep.
Should be a link in the description box.
Also, if you like this video, please subscribe and like. It only takes a few seconds and it's completely free and it'll help us out a lot. See you next time.
Have a good day.
Bye.